Okay, question 5. A point charge Q creates an electric potential of plus 125 volts at a distance of 15 centimeters. What is Q? Okay, simple question. For potential of point charges, we just use the formula V equal to K Q over R. So that means you've got a certain point charge here, you're a certain distance R from it, and then the potential at that point is given by this. Potential, just like potential energy, you cannot specify it unless you specify a reference potential. Like, you can't just say the potential energy is 30 joules for something. That is meaningless in of itself. You've got to specify where's the reference potential energy. Where is the reference potential energy of 0 joules? Same thing with potential. If you want to talk about the actual potential, instead of just potential differences, which is fine to talk about, even without specifying a reference, but if you want to talk about the actual potential, at any point you've got to specify a reference. But if we're dealing with a point charge or point charges, and then the potential at a specific point, then the understanding is that the reference potential is infinitely far away from this whatever collection of point charges you're looking at. Infinitely far away, where there is negligible electric forces being felt due to these point charges. So the potential here is plus 125 volts. And that means it is 125 volts more than it would be at any point, infinitely far away from this charge Q. Okay, so for point charges, that's important to understand that the reference potential of 0 is infinitely far away. Okay, so let's calculate this. Okay, wait, what's the actual question? What is Q? So ask what is Q. They give us V, K we've got, that one we're used to, and R is given as 15 centimeters. Okay, and let's get Q by itself. So Q is Q is equal to, why is it getting bright like this? Oh, I see. Okay, 1 second. That should be better. Okay, so Q is equal to VR over K, and now we just substitute. What is it? 125 volts. What is R? 15 centimeters. 15. Where is now? 15. Okay, so it's 0.15 meters. Only two significant figures given. And what is K? Oh, okay. Now we can use 8.988 or whatever. It doesn't really. In this case, it's definitely perfectly fine to use this one. And now this is Newton meter squared per coulomb squared. Now let's just calculate this. So that's 125 times 0.15 equals divided by 9, so times 10 to the power minus 9. Okay, like that. Okay, so that is, I'm going to provide two significant figures for my answer. So how much is that? 2 point something times 10 to the minus 9. That's nano. So this is 2.1 nano. And what is it? Charges, it's coulomb. So it is Newton coulomb. Okay, that's it. Well, while we're at it, while we're on the subject, let's do question 6 as well. Now for question 6, it's also asking for the potential at a certain point A. What's the potential at the fourth corner, this one, with these charges at arranged like this at the other points of the square. Now it's not a single point charge, now it is several. And they also talk about taking v equals 0 at a great distance. Okay, now this part, taking v equals 0 at a great distance, this is just stating what we already are assuming for potentials around point charges. This is what I explained here in infinitely far away, the potential is taken as 0. So that is just restating that. And so that's fine, that's nothing new. But now, how do I deal with the case of its multiple point charges? Now, this is quite simple actually. Let's the potential at A is going to be equal to well, let's say that's 1 and that is 2 and that is 3. Okay, let's say, so that's point charge 1, point charge 2, and point charge 3. Now, the nice thing about working out potentials due to point charges, if they're more than one, is you just add all the potentials all together. This is what I mentioned at the end of the lecture notes. If there are multiple charges present, simply calculate and add the potentials due to each. So the potential there at A will be the potential at A due to that charge, which is going to be, let's call that V at A due to 1. And it's going to be plus the potential at A due to charge 2, plus the potential at A due to charge 3. Okay, now what is the potential at point A due to this charge 1? Okay, now we just use the same formula again. Just use the same formula again, KQ over R. So K, and what is Q now? If it's that charge, it is 3Q. And what is R? What's the distance? It is L. Okay, plus K, Q. What is Q now? I'm not looking at the second charge. It is minus 2Q over L. Plus, again K, now third one, that's just Q over, and now what is this equal to? What is this distance? What's this distance? That's going to be the square root of L squared plus L squared due to Pythagoras. So L squared plus L squared is 2L squared. You take the square root of that, you're going to get L times the square root of 2. So square root of 2L. That's it. Okay, there you have it. Now you just have to simplify it. So let's simplify that. It is equal to, well, let's just take out a bunch of common factors. I can take out KQ. Let's take KQ. Well, let's take KQ over L out. That's a common factor. So then what do we have? First term is 3, then minus 2, and then plus 1 over the square root of 2. Okay, now we just simplify that. So that is KQ over L, that is 1 plus 1 over square root of 2. Let's add enough steps to explain nicely what we're doing. So let's write this as KQL over square root of 2 over square root of 2. Okay, now I'll just skip that step, square root of 2 plus square root of 2. Like that. And yeah, I think that is simplified enough, and then that is good enough for your answer. So, just to recap what happened, if only that charge was there, if those two weren't present, then that would be the potential. That term would represent the potential at A. If only that charge was present, not those two, then this term here would represent the potential at A. If only this charge was present, the other two weren't there, then the potential at A would be given by this term. But because all three of them are present, you can just add them. This was given to you that this is how it works for point charges, but the potentials of point charges. Due to all three are being present, you just add the potentials of each to get the potential at the point. So this here is an expression for the potential at point A. Okay.